Hello everyone, welcome to lecture number 4 of the 4th week. In this lecture, we will explore Raabe test, the another test when D'Alembert ratio test fails. So in the last lecture, you have learned about D'Alembert ratio test, in which we have find out that if we have a limit n tends to infinity un plus 1 by un is equal to L, then the whole series convergence and divergence depends on this limit. This limit is less than 1, the series is going to be divergent. But what happens when L equal to 1? We do not know what happens because the test fails at this L equal to 1. Once test fails, then we use another test, we call it Raabe test. So one superior test is the Raabe test, and once ratio test fell, then we use the Raabe test. So here we will prove mathematically Raabe test with the statement. So what is the statement? Consider positive term infinite series capital sigma un and the limit. Now you can pay attention on this one. In the first one, D'Alembert ratio, we had un plus 1 divided by un and limit n tends to infinity, right? That is equal to L. But here in the reverse way, so that's why in that case we have summation un converges if L is less than 1 and diverges when L is greater than 1. This is a D'Alembert ratio test, right? Remember this one. Now since I have changes or reverse this order, that is un divided by un plus 1 into minus 1 into n, then the convergence and divergence criteria has been changed. So that is one important thing you have to understand. So here if I evaluate n un plus 1 minus 1 is equal to L, then it is the series is converges if L is greater than 1, diverges if L is less than 1, and then again test fails when L equal to 1. Once test fails, we need some superior test to investigate its convergence or divergence. So proof, consider case 1, that is limit is greater than 1. So since limit here is 1, this is 0 and this is L. Since limit L is greater than 1, I can subtract this one L minus epsilon, arbitrary epsilon, and such that it is going to greater than 1 and L minus epsilon, let its name is as alpha. So I have alpha which is L minus epsilon and which is still greater than 1. That's our criteria. Now since limit is given, the definition of limit is given, so limit n tends to infinity n into un divided by un plus 1 minus 1 is equal to L is given. So using the definition, of limit, if it exists, that means for given epsilon is greater than 0, there exists a natural number, let us say m, such that the whole this term, that is n into un divided by un plus 1 minus 1, lying in the neighborhood of L plus epsilon and L minus epsilon. This is the epsilon neighborhood of L point, right? Now take consideration of the right hand inequality. So this inequality I will take, the left hand one, right? So let me erase first. So I have to erase this one and then take this, right? So we have to take the left one because we have considered L minus alpha is L minus epsilon which is greater than 1, that's why. So consider this one, what it will give you? This will give you L minus epsilon is less than n into un divided by un plus 1 minus 1, right? So simplify, this is n into un minus of n into un plus 1 and divided by un plus 1, and here is L minus 1. So I mean take this other side, so you will get this is alpha, so you will get alpha into un plus 1 is less than n into un minus of n un plus 1, right. Simplify it and take this here. So this will comes out to be this term, right. So it will comes out, take this here. So this will comes out alpha plus of n. So this will comes out alpha minus of 1, alpha of minus of 1 here into un plus 1 into un plus 1 and here n into un minus of n plus 1 un plus 1. I think I will derive for you. So let me erase these things, and now we have to derive in our own way, right. That will be help us. So this will comes out to be L minus epsilon into n un minus n un plus 1 and divided by un plus 1, which is less than L minus epsilon. So alpha into un plus 1 is less than n un minus n un plus 1. That is the things here, it's written here. Now do the same thing. You have to subtract and add un plus 1 both sides. So subtracting here, so we have alpha un plus 1 minus un plus 1 is less than n un minus n un plus 1 minus un plus 1. I can subtract this both sides, right. There is no difference, or there is no effect. So this will comes out alpha minus 1 into un plus 1 is less than n un minus of n plus of 1 into un plus 1. That is here, right. Now remember this one, alpha is greater than 1. So alpha minus 1 obviously greater than 0, right. So this term is going to be greater than 0. So this term is a positive, and putting the value. So here we had alpha minus 1 un plus 1 is less than n un minus n plus 1 un. So I am writing for you here. So n un minus of n plus 1 un plus 1 is greater than, right, is greater than alpha minus 1 un plus 1. Now put n equal to m first. So it will comes out to be m um minus of m plus 1 um plus 1 is greater than alpha minus 1 um plus 1, right. And now put m plus 1. So this will comes out m plus 1 um plus 1 minus of m plus 2 um plus 2 is greater than alpha minus 1 um plus 2, right, and so on. You can put till n minus 1. So putting n equal to m plus 1, m plus 2 and n minus 1, and adding all those, you have to add this one. So see the here, m plus 1 is positive here and m plus 1 is negative here. Similarly this one is going to be in the next term. For this one is going to be this term. So what you will get? You will get the first term here and the last term here. So mum minus of nun is greater than alpha minus 1, and add all those quantity here. So you will get um plus 1, um plus 2 and till how much? Un. So this will comes out to be, now I think you have remembered this one, that for a series un, Sn is equal to u1 plus u2 plus so on plus of un, and Sm is equal to u1 plus u2 plus of um. If n is greater than m, then you have here in the intermediate um plus of um plus 1 plus um plus 2 and so on till un. So you will cancel out till this one. So what it will remains? It will remains um plus 1, um plus 2, un. So this um plus 1, um plus 2, um plus 3 till un can be written as the differences, sum of partial sums of Sn minus Sm of that series, right. So that will be okay. And then adjust this one. So you will have here MUM minus of NUN, which is greater than alpha minus 1 into SN minus SM, right. So take SN as a sequence. So take SN is equal to how much? This will comes out to be SM plus M divided by alpha minus 1 into UM, and this will happen for every n is greater than M. So that means since this is a fixed quantity, this is a fixed quantity, right. So that means Sn is bounded above and Sm is a finite number. Thus Sn was the partial sum of this series. So nth partial sum, the sequence Sn is bounded above, and since the series is of the positive terms, so therefore it is monotonically increasing. So Sn is also monotonically increasing. So a monotonically increasing sequence bounded above must be convergent, and henceforth since Sn is convergent, therefore the whole series is convergent. That is the proof, right. Similarly, consider case 2. So here we have L as less than 1. So L is less than 1. So if I choose L in such a way, or if I choose epsilon in such a way that addition of this epsilon in the limit does not affect its qualitative behavior, that means it is still less than 1, that will be okay, right. So let us choose this one. So L plus epsilon is now less than 1, and if you remember this inequality here, the right side of this inequality. So use this inequality. What it will give you? It will give you NUN minus NUN plus 1 divided by UN plus 1 is less than L plus epsilon, which is less than 1. And this means UN divided by NUN minus of NUN plus 1 is less than UN plus 1, right. And that means UN divided by UN plus 1 is less than N plus 1 divided by N, right. Just inequality doing the same, and this is happen for N is greater than equal to M. So taking Vn as we can write this one, UN divided by UN plus 1 is less than Vn divided by Vn plus 1, where Vn is nothing but 1 beta n. So in that case the series Vn, this is the series Vn. Series Vn is a diverging series, and by comparison test each nth term of the two sequences Un and Vn, two series Un and Vn is less than. So by comparison test of the first type, this series is diverging because the series Vn is diverges, right. So that was the proof for L is less than 1, L is greater than 1. Now what are the counter example for L is equal to 1 where test does not imply, test fails? So let us choose two known series. One is summation 1 by n. So this series is a diverging series. We had already seen this one. And another one, series n log of n square, and this series is a converging series. So using this to calculate limit of n into Un divided by Un plus 1 minus 1, and this will comes out to be 1 in both of that series, and henceforth we cannot conclude the series is convergent or divergent when limit become 1. So test fails here, right. That is the proof, whole proof of this test. Now we can use the another statement. Some of the authors uses this statement, and that is totally right. You can prove this very easily, that if Un be a positive term series such that limit n Now this is the reverse one, un plus 1 by un minus 1 is equal to L. Then it converges. If L is less than 1, it is diverging, but L is greater than 1 and test fails at L equal to 1. You can prove by the similar approach. There is no need to prove another similar type of things. So you can just go and prove it. Now look at the structure of the problems and solution using the Raabe test. So before using the Raabe test for a given problem, you need to calculate or use the ratio test. Once the ratio test fails, then you have to use the Raabe test. So test the convergence of the series alpha by beta plus 1 plus alpha 1 plus beta 1 plus alpha into 2 plus alpha and so on. So what will be the nth term of this series? The nth term of the series is going from the numerator 1 plus alpha 2 plus alpha to n minus 1 plus alpha, and denominator in the same way plus beta, right? As you can see here, this is the third term. So 2, that means n minus 1 here, right? So once we have, then we are going to use firstly ratio test. To use the ratio test, we need to calculate limit un plus 1 by un. So calculate this one, and this will comes out, everything is going to be un plus 1, that means what? 1 plus alpha into 2 plus alpha till how much? N plus alpha divided by n plus beta and so on, 1 plus beta, 2 plus beta and so on, right? And this is un plus 1. So what is the un? Un is 1 plus alpha, 2 plus alpha and so on to n minus 1 plus alpha divided by the similar thing 1 plus beta, 2 plus beta and so on. How much? N minus 1 plus of beta. That's right. So cancel it out, cancel each term of the denominator, and you will find out there is only two terms, that is n plus alpha divided by n plus beta, and take n outside. So this will comes out to be 1 plus alpha by n divided by 1 plus beta by n. So this will be 1, right? So limit is 1. Now since D'Alembert's ratio test fails when limit is 1, I need to use the superior test, and that test is the Raabe test. So calculate the Raabe test, limit n into un by divided by un plus 1 minus 1, and this will comes out very easy to calculate it. How? We have already find out un plus 1 by un equal to what? Alpha plus beta, n plus alpha divided by n plus beta. That means un divided by un plus 1 is n plus beta divided by n plus alpha minus 1. Just simplify it. This will comes out beta minus alpha divided by 1 plus alpha by n. So this will comes out to be beta minus alpha. So now the convergence of the series depends on this limit. So limit the series un is converges if beta minus alpha is greater than 1. This means beta is greater than 1 plus alpha, right? And series is diverging when beta minus alpha is less than 1. So beta is less than 1 plus alpha, and when beta is equal to 1 plus alpha, the test fails. So test fails. This diverges and this converges. So I have to choose what happens if I put beta equal to 1 plus alpha. Now look at the given problem. This is alpha by beta plus 1 plus alpha divided by 1 plus beta plus 1 plus alpha and so on. So in place of beta, we have to put 1 plus alpha, right? So to do this, what it happens? This will become alpha divided by 1 plus alpha plus 1 plus alpha divided by 2 plus alpha and plus of so on, right? So this will comes out to be series of 1 plus alpha divided by n plus alpha, and this is nothing but you can compare this series as series 1 by n, and series 1 by n is what? Series 1 by n is a diverging series. So by comparison test we will have the diverging. So now the whole series un converges when beta is greater than 1 plus alpha, and it is diverging when beta is less than and equal to 1 plus alpha. That is your answer. Now look at the second problem. So it is given, un is given, un is this quantity 3.6.9.3n divided by 7.10.13 to 3n plus 4 into x to the power n, and x is a positive quantity, right? And we have to prove that this series is converges for x is less than or equal to 1 and diverges for x is greater than 1. So now we are going to prove this. To prove this, firstly we have to calculate ratio of the two terms un divided by un plus 1. So this will gives you 3n plus 7 divided by 3n plus 3 into 1 by x. That is the important things, right? So taking limit, so what will be the ratio test? Ratio test means I have to calculate limit un plus 1 divided by un, and this will comes out to be 3n plus 3 divided by 3n plus 7 into x. So in a limiting sense, in the limiting sense. So this will comes out to be limit n tends to infinity 3 plus 3 by n divided by 3 plus 7 by n into x. So this will comes out to be 3 cancel out. So this is 1. So this is x. So this limit is going to be x, right? So that means if x is less than 1, then the series un is converging by ratio test. This is the ratio test, right? D'Alembert's ratio test. And if x is greater than 1, series un diverging, and x equal to 1, test fails. So now put x equal to 1 in the problem, right? Test fails. So now put the x into 1. So what it will give you? This will give you limit of un divided by un plus 1 is equal to limit of 3n plus 7 divided by 3n plus 3, and this will be going to be, this will be 1, right? But we need to calculate limit n into un divided by un plus 1 minus 1. So that's why limit of n tends to infinity n into un plus 1 is calculated here, 3n plus 7 divided by 3n plus 3 minus 1. So this will comes out to be 3n plus of 4, right here going to be there. So minus of 3n. So this will going to be 4, right? So 4n divided by 3n plus 3. Okay, so now I have to calculate this one for you. So this will comes out to be n into 3n plus 7 minus 3n minus 3 divided by 3n plus 3. So 3n cancel out, and this will be 7 minus 3 is equal to 4, and this will be n here. So that means 4n divided by 3n plus 3. And taking limit n tends to infinity will give you 4 by 3. 4 by 3 is greater than 1. So that means Raabe test converge. By the Raabe test, series is converging. So now we can conclude that series is converges x is less than 1 as well as x equal to 1. So the whole series un converges when we have x is less than and equal to 1. And since it is greater than, so this will be 0 is also here, and divergent for x is greater than 1. That's the proof. Now look at the problems. The last problem, I believe, test the convergence of the series 1 beta nq, right? So calculate un divided by un plus 1. un divided by un plus 1 will give you n plus 1 ka whole cube divided by nq, right? So this can be written as 1 plus 1 beta n ka whole cube, and this can be written as 1 plus 3 by n plus of 3 by n square plus of 1 by n cube and so on, right? So calculating n into un divided by un plus 1 minus 1, it will comes out n into this quantity. So this will comes out to be n into this quantity. So this will comes out to be 3 by n, 3 by n plus of, using this minus 1. So minus 1 cancel out. So this will be comes out to n in n. So 3 is here, 3 by n square, and take the limit, limit will give you 3, and 3 is greater than 1, therefore the series is 1 beta nq is convergent. Can you recognize that this series is a P series, and P is greater than 1 and P is greater than 1, that means it is convergent series. So that's what we had proved by the Raabe test as well. So here I am going to end this test. You had only 4 tests to proof, a state and proof, and then you have some problem related to that problem. In the next lecture I will explore some more problems, different type of the problems, and a stronger test. When Raabe test fails, Gauss test will come in a picture, but there is no proof for that because it is out of the scope of the syllabus. So thank you so much.